Hello, this is part 3 of homework 1, vectorization, Jacobian, Frenet-Serre, 3D plotting, where I am getting some better camera angles and me explaining things. So I need to, in part 3, explain and code a function that calculates, that's not a word, a surface point at distance radius equals 0.5 from the central helical curve for an arbitrary angle theta between n and the cross product of t times n. Why is it necessary to use the cross product of t times n? So basically I need to get a function that makes a surface point at a specified value of t and of theta. And the t isn't necessarily said here, but it's implied, but the angle theta. So what does any of this mean? What am I trying to get at? Well, let me go into Paint and I will explain it very quickly. So if I go ahead and delete that all and maybe go back to a brush, let me say that I have just a plot, and just a two-dimensional plot, and I have a certain circle on that plot, and I'm plotting it maroon because maroon's a cool color. How would I maybe say get this point right here, like get its coordinates? Well, I could maybe take a radius of the circle and then some angle theta, and then I would know the coordinates of that point, which maybe I'll color it in blue, are just going to be the x is going to be that radius times cosine of the angle theta, and then y similarly is going to be r times sine of said angle theta. So this is all cool. These are like the x and y coordinates of that angle theta. But let's say, how do I get like this plane that r and theta are built on? Because that's sort of what we're going to do here, but then I need to get a plane somehow that r and theta are going to exist on. Or that this circle is going to exist on the plane, rather. And that's where Frenet-Serre comes in. Because Frenet-Serre is telling us we have this tangent, we have this normal, we can take the cross product of those two to get b, and then you can do vector multiplication between n and b, and like n will give you the x values of the plane, and b will give you the y values, or either or. It doesn't really matter, honestly. But yeah, you can use these two vectors, which are both perpendicular to the curve, to build a plane that is always perpendicular to the curve at a specific point. So this is really powerful for what we're trying to do, right? Because if I go back to the beginning, I have this curve. I want to build like a bunch of circles around it. In fact, I could even go this way, maybe? Yeah, that's what I'm trying to do, build a bunch of circles around the plane. So that's sort of what I'm trying to accomplish here, and that is why I need to use the cross product of t and n to make a plane that I can plot the points in. But anyway, if I were to go back to here, let's look at this again. So we talked about it a little bit. I need to take these coordinates defined by the n and b values from the Frenet-Serre, and I want to do a matrix multiplication with this stuff up here. So I want to put this stuff in here and get like an x and y value, and then that's a terrible y, and then when I do that, I'm actually going to get sort of the answer I'm looking for. And I'm making sure not to color around, or not to draw around my face cam down here, or I guess the side cam on the other side. It's kind of funny. I don't know. Hopefully it looked like I was kind of looking at the camera there. I don't know. I think it's cool. But anyway, we have these two vectors. We have the x and y coordinates. This is actually going to give us the points for the circle. Or I guess for right now we are just doing. There's another C in circle. But for right now, I'm just going to get 1 point at a time, and then I'll go through and get like all these points on the surface. So with that, let me hit save, just to, I don't know, save. People make fun of my background. They think it's kind of lame or something like that. I don't know. But anyway, I can go ahead, close this. The Jacobian's okay. Frenet-Serre is okay. So this is like the surface points function I'm about to code out. I'm going to get the tangent and norm from Frenet-Serre. I'm going to define these t and theta values. Actually, I don't need to do this, so I probably won't do it. And then I'm just going to make a function to calculate points at a specific time and theta along the surface of this plot. So it would be like a single, I'm not using those, I just accidentally clicked on those. But it would be like a single, where am I looking? I've almost got it. It's in Paint. That's why I can't find it. But like at a single point, like it would be, I don't know, like it'd be like getting a point right here, or a single point right here, depending on t and theta. So that's pretty cool, and then I'm just going to put it all together using some of these vectors, and yeah, but anyway, let me delete this, and let's go ahead and maybe define the surface function. And what do I need to give the surface function? Well, okay, shoot. Let me restart the runtime. Well, let me restart and run all, because I just don't want to make it seem like I'm getting any hints from having the thing already filled in. But I define surf as a certain function, but I need to pass into a couple of variables. So I need to give it a value of t, and then also a value for theta. So that way, t lets it know at what point along the curve. So like basically t tells me what circle to choose. So like t tells me, should I put it on this orange circle, this one, any of these? And then theta tells me where along the orange circle to put it. So theta is like an angle. T is just, sort of like the t that I generated before. So I could go ahead and generate t and theta values, but I won't. I'll hold off on that. Now, before I do that, let me go up here to frene and just make use of the tangent and norm functions. And I will go ahead and say tangent and norm are just equal to the things from frene. So that's just important to have that information. So now I have this function for surf, and let me go ahead and just to make things a little bit shorter, I will go ahead and define t, so the tangent, as this tangent function evaluated at point t. And then similarly, I will define n as the normal function evaluated at point t. And then also b will be the cross product. So what is the cross product? Well, Jax has a cross product built into it, so I'll probably end up using that. But jax.numpy.cross, so I could say jnp.cross. It wants a vector a vector b, and then some other stuff that I don't need to do for this situation. So I can just go ahead and say, I will change this all to jnp. jnp.cross of t and n. Sweet. So now I have t, n, and b values, and now I need to start thinking about what do I want to return. Well, I just want to return an x, a y, and a z, or z, if you're from Canada, value. And if I can get this to work, there it is. So I want to return an x, y, and z value from here, and I want to return it in the form of like a matrices, I think, or an array. I meant to say array. And so we have this t, n, and b. I will go ahead and define like the surface coordinate radius, so r equals 0.5. So that's like just the distance between the center of the curve and the surface coordinate point. And so what do I need to do here? The x, y, and z was just kind of there for me to talk through it a little bit. Well, if I go back over here to what I drew out a minute ago, I need to take n and b. So I need to somehow like zip or stack, hint hint, these two arrays, n and b, together. And then I also need to get an array of these two functions up here. And then I need to do a matrix multiplication, which in NumPy, or in Python, rather, not NumPy, is an @ symbol. So all that's said and done, let me go ahead and maybe start off with stacking these n and b together. Unfortunately, I have some documentation up right here. So jnp.stack. It needs a list of arrays, right? I think the arrays, yeah, sequence of array like, so it needs to have a bunch of arrays with the same shape. I already have that with n and b, they're the same shape. And then I need to give it an axis. And so axis, it wants an integer, which I guess for this case would be 0 or 1, or I guess it could be any number of integers, but it's basically telling me along what axis should I stack these values. So I actually want to stack these in the y-axis, so I'm going to set axis equal to 1. That's just what y-axis means here. And so I will return, maybe, what is this documentation? Just copy that, go ahead and turn that into J and P, even though I don't really need to. I already imported Jack, so I'll just go ahead and turn it into J and P. So J and P stack, I need to stack together N and B, which I believe for this, yeah, I think I need to give it a sequence of arrays. So I believe, if I remember correctly, I need to give it like the arrays as a tuple, like this. And then, so I'm stacking those two arrays together along the x, or along the y-axis, and then I'm going to multiply that, or do a matrix multiplication by, what do I have over here? By these x and y functions. So r cosine of theta, r sine of theta. Well, that's not too bad to do. I'll just say that np.array, and say that the first array for the x value is going to be r times cosine of theta. And then, similarly, I might just go ahead and copy this, copy it, comma, paste, and then the y value is just going to be from sine of theta. So with that, I think I have everything I need to go ahead and run the function. And this isn't entirely correct yet, but let me just go ahead and try to demo it with some points. So we have this surface function of t and theta. Surf, I need to give it a t and a theta value, so I'll just say maybe when t is equal to 0, and also say when theta is equal to 0. And remember, these need to be floats, so that's why I'm putting the decimal point on there. That's something that screwed me up for several minutes when I was practicing this. I just kept looking at it like, what is the issue here? It should be right, and it's like, yeah, well, you need to have decimal points. So if I go ahead and run that, I will get an array. And this array doesn't quite make sense if you really think about it, because look at this. It's saying that if I go back up here, this is the curve, right? So when t equals 0, this is the point on the curve. I want to point at theta equals 0, so it should be somewhere around, actually no, it should be somewhere out here, kind of where my cursor is right now. But instead, we see a point at, at 0 and 0 in the y and z axis, which makes sense. But then it's at negative 0.5 in the x-axis, which is all the way over here, sort of like on this bottom plane down here. And that just doesn't seem right, right? We should see a point like somewhere in this area. And the reason is because I'm not returning the surface point here. I'm returning the relative coordinates of the surface point right now, because I'm just taking, this is just the, I guess I should have probably made this a little bit more clear. It's the relative. I'm not telling it where the, I'm just telling it a plane on the curve. I'm just telling it a plane that is perpendicular to the curve. I'm not telling it where on the plane to go. So if I go back here, it's pretty easy to fix. I will just go ahead and say, I will add curve at the point t to that. So now I'm giving it a point to start at. So start at these curve x, y, and z values, and then add on to that the product of what we have down here, this thing. So if I go ahead and run that, run the surface vector again, I will get a much more sensible value. So the device array is at 2.500, and sure enough, if you look right here, when t equals 0, you would expect there to be a point about right here when theta equals 0, and then you'd also expect there to be points all around here. And so that's what I'm going to get into in the next video. I'm going to do part 4, vectorize the function, and generate a plot of the surface points around the helical curve. So with that, I have finished up part 3. I explained and encoded a function to calculate the surface point at just a single point. And next time I'm going to turn that into a full, just a full array. So thank you for watching, and I will see you in the next one. Bye-bye.